Hey everyone, welcome back to BK's Tech Stack. Today, we're taking a deep dive into the fascinating world of advanced generative AI, exploring the models and architectures that make it all possible. Let's get started. So, what are we talking about when we say generative AI? Basically, it's AI that can create things. Instead of just identifying objects in an image or translating text, it can actually generate new images, new text, new music. Imagine an AI artist. It doesn't just recognize art, it makes it. The key thing here is that it learns patterns and then uses that knowledge to produce something truly original. Let's use a simple analogy to make this clear. Imagine generative AI as a chef in a kitchen. The ingredients are all the data it's seen, every image, every piece of text. The recipes are the algorithms it uses. Now, a regular chef follows a recipe, but our Gen AI chef, they can take those ingredients and recipes, experiment with them, and cook up entirely new dishes you've never tasted before. That's the generative magic. So what does this actually mean for you and the world around us? Generative AI isn't just a cool tech demo, it's a game changer. It's helping marketing teams brainstorm fresh ideas for social media, powering chatbots that instantly answer your questions, and even creating personalized shopping experiences online. For industries like automotive, it's designing better car parts faster. It's a fundamental shift in how we create and interact with digital content. Here's the key thing you need to remember. Traditional AI is great at understanding and making predictions from data. If you show it a picture, it can tell you if it's a cat or a dog. Generative AI, on the other hand, can actually draw a new cat or dog. For something like language translation, traditional AI uses statistical rules. Generative AI, with its deeper understanding of language patterns, can generate much more natural and contextually appropriate translations. Let's understand this step by step. When we talk about AI, machine learning, and deep learning, we're essentially looking at a family tree. AI is the big umbrella. Machine learning is a branch where computers learn from data. Deep learning is a specialized, powerful technique within machine learning that uses neural networks. And it's within deep learning that generative AI really finds its roots, leveraging these complex networks to create amazing new things.
Now, at the heart of deep learning, and by extension generative AI, are neural networks. Think of them like digital brains. They're made up of layers of interconnected neurons that work together. Data comes into the input layer, gets processed through hidden layers where the real magic of pattern recognition happens, and then a result comes out of the output layer. These networks are how AI learns to think and create.
There are different flavors of neural networks, each good for different tasks. FNNs are straightforward. CNNs are superstars for images. RNNs are brilliant for anything with a sequence, like language. Autoencoders are great for making data smaller and finding odd patterns. And then we have transformers. These are the models that really kicked off the advanced generative AI boom, especially in language, by fundamentally changing how we process sequences.
RNNs are crucial for anything sequential, like language. Imagine reading a book. You need to remember what happened chapters ago to understand the current paragraph. That's what RNNs do. They have a kind of short-term memory that lets them process words or events in order, building context. And for really long stories or complex sequences, we use souped-up versions like LSTMs and GRUs, which are even better at remembering things over extended periods.
So, where do you see RNNs in action? A perfect example is speech recognition. When you talk to your phone, an RNN is working behind the scenes. It's taking your continuous audio, which is just a sequence of sounds, and breaking it down, remembering the previous sounds and words to understand the full context. That's how it converts your spoken words into text, accurately, even when you speak naturally. It's what makes your virtual assistant so helpful.
Next up, we have autoencoders. These are pretty clever. Imagine you have a huge, detailed photo. An autoencoder's job is to compress that photo down to its absolute essence. We call that the latent space. And then, using that essence, reconstruct the original photo as perfectly as possible. The beauty is, by doing this, it learns what truly matters in the image, making it fantastic for things like reducing file sizes or finding anomalies.
A great practical example of autoencoders is image denoising.
Imagine you have a blurry or noisy photo. An autoencoder can essentially clean that image. How? We train it by feeding it noisy versions of images and telling it what the clean version should look like. Over time, it learns to recognize and remove the noise while keeping all the important details. This is super helpful in areas like medical imaging or restoring old family photos. Now, VAEs, or variational autoencoders, are a special flavor of autoencoders. The main distinction? They're built for generating new stuff. While a regular autoencoder compresses to a single point, a VAE compresses to a range of possibilities, a distribution. This probabilistic twist is incredibly powerful because it means you can sample from this range to create endless new images or data points that are similar to what it's seen, but completely original. It gives us more control over the generated output.
So how do VAEs make a difference? Beyond just cleaning up images, they're fantastic for efficient image compression. Think of it like a magical photo album. You put your high-resolution pictures in, and it smartly compresses them. When you want to see one, it recreates it perfectly, saving storage space. But the really cool part is, because of their probabilistic nature, VAEs can also generate completely new images that fit a certain style. This is huge for things like speeding up websites, and even for digital artists creating new designs. Now, let's talk about GANs, or Generative Adversarial Networks. These are pretty revolutionary. Think of it like an epic game between two players. You have a generator that's trying to create fake images so good they look real, and you have a discriminator that's trying to sniff out those fakes. They constantly train against each other, getting better and better, until the generator can produce incredibly realistic data that even the discriminator can't tell apart from the real thing. A notable real-world impact of GANs is deepfake technology. We've all heard about deepfakes, right? Basically, it's about creating incredibly realistic but fake videos or images where someone's face is superimposed onto another person's body. The generator in a GAN is the one creating these sophisticated fakes, while the discriminator acts as the detector. This adversarial process makes deepfakes unbelievably convincing. While there are ethical concerns, it's also revolutionizing special effects in film.
Now, let's talk about transformers. These models have absolutely revolutionized NLP, or natural language processing. The game changer here is something called the self-attention mechanism. Instead of processing words one by one, like RNNs, a transformer looks at all the words in a sentence simultaneously and figures out how important each word is in relation to every other word. This allows for incredibly efficient processing and a much deeper understanding of context, even in very long sentences.
Where do you encounter transformers every day? Language translation. If you've ever used Google Translate and been impressed by how natural the output sounds, you're experiencing transformers at work. Traditional translations struggled with context, but transformers look at the entire sentence to understand the meaning before translating. This means they don't just swap words, they convey the idea more accurately, making cross-language communication smoother than ever.
So, how does all this magic happen? It's a multi-step workflow. First, we train the model by showing it huge amounts of data. It learns the patterns, almost like a student studying. Then, once it's trained, we can ask it to generate new content by sampling from what it's learned. This is where the AI gets creative. Finally, if we want it to do something super specific, we fine-tune it on a smaller dataset tailored to that task, making it even better at specialized jobs. Once we've trained and fine-tuned our models, how do we know if they're actually good? We evaluate them based on 3 key factors: speed, diversity, and quality. If your AI generates something for real-time use, it better be fast. It also needs to be diverse, producing a wide range of unique outputs, not just the same few things over and over. And of course, the output needs to be high quality, realistic, and useful. DALL-E is a fantastic example that excels in both quality and diversity, creating incredible images from text. Generative AI is a rapidly evolving field, and there are some really exciting trends emerging. We're seeing cross-model learning, where different AI models share knowledge, making them even smarter. Few-shot learning is about training powerful models with very little data, which is a huge step forward. And of course, responsible AI development is front and center, ensuring these powerful tools are used ethically.
The innovation in new architectures is constant, so expect even more amazing things.
All right, that's a wrap. Remember, generative AI is all about creating. We've seen how models like RNNs, autoencoders, GANs, and transformers do this, and why evaluating their speed, diversity, and quality is so important. This field is changing fast, so keep learning and exploring.